shown in figure below, operates from a DC source, and applied sinusoidal input signal generates a peak base current of 99 milliamperes. So IBEM, that is the peak base current value, M stands for maximum, is 9 milliamperes. Okay, so calculate quiescent collector current. Quiescent collector current is ICQ. Then quiescent voltage VCEQ. DC power input PIDC. AC power output P naught AC. Efficiency. Assume beta is equal to 50. VB is equal to 0.7 volts. All right. So this is the question. It will come for 6 marks to 8 marks. Okay. Very typical problem. Solution. First, you can start with finding out the DC values. Okay. So whatever I have marked in star, they are basically the DC values or the operating point values. Okay, so first let us calculate ICQ. In order to find ICQ, you need to know IBQ, right? So what is IBQ? Power supply voltage minus transistor threshold voltage divided by base resistance RB. So that's 20 volt minus 0.7 volts divided by 1.5 into 10 to the power 3. Okay, so that is about 12.87 milliamperes. Okay, so that is IBQ, and therefore you can find ICQ. ICQ is beta times IBQ, so that's 50 times the base current value. Okay, and that is 643.5 milliamperes or 0.643 amperes. See, you can clearly observe in your small signal transistor, the base current used to be in the range of micros of amperes, and your collector current, usually it used to be in terms of millis of amperes. However, in case of power amplifier, you can see the level, okay, at which the base current flows is at milliamperes, and the collector current will be in few amperes, say 0.643 amperes. So that is actually nothing but the power magnification. So your power amplifier can handle large collector and collector current swings and voltage swings. Okay, so that's the first part of your problem. The second part is about VCEQ. So what is VCEQ? VCC minus drop across the collector resistor, right? Or the load resistor, because RL is equal to RC. Just right, which is equal to RC. Okay, so that is 20 minus ICQ is 0.043 into RL, which is 60. Okay, so that is 9.7 volts. Okay, that is 9.7. So you're done with ICQ, then VCQ. Now let us look at the third part, PIDC. So PIDC is nothing but it is totally the DC values. So VCC into ICQ, 20 into ICQ. ICQ is 0.643. Okay, so that is roughly about 12.87 watts. Okay, so that's your PIDC, and then you can find out P naught AC. Okay, so P naught AC, okay, we can basically write, RMS square into RL, right? Now, but what is IRMS? Because RL is known, which is 16 ohm. IRMS is unknown. So you cannot directly write a value for IRMS provided you derive that particular value. Okay, now how do I get the RMS value? Now, if you look at the problem statement, it's been given that the maximum value for base current is 9 milliampere. So therefore, maximum value for collector current is beta times the maximum value of base current. IBM. So that is 50 times the maximum value of base current. How much is it? 9 milliamperes. Okay. So that is 450 milliamperes. Okay. 450 milliamperes. So that is the maximum value. Now RMS value. Therefore, we can say IC RMS is equal to IC maximum divided by root 2. That's 450 divided by root 2 milliamperes. Okay, and that is about 318.19 milliamperes. Okay, now this itself is your IRMS. Why? Because the ICRMS itself is your IRMS, because the collector RMS value of AC current is nothing but the load current. Hence, ICRMS, we have taken it as IRMS itself. All right. Hope you are clear about it. Fine. So, therefore, P naught AC is equal to, let me write it once again, IRMS square into RL, or 0.31819, because milli is 0.31819 square into RL. RL is 16. Okay, and that is 1.619 watt. Okay, that's just 1.619 watt. So therefore conversion efficiency is P naught by Pi. Output is 1.619 and the input is 12.87. Okay, into 100, and that is 12.58%. Okay, so that's the conversion efficiency. So in bracket, let me write, okay, whereas the possible eta max would have been 25%, but how much you are getting in reality? Just 12.5%. Okay, let me just add some add-on questions. Power dissipation. Say, for example, power dissipation, if at all it is asked. Okay, what is power dissipation? Power dissipation is nothing but the waste power, okay, which has not taken part in the energy conversion, right? So power dissipation is input minus output. So input is 12.87 minus output is 1.619. Okay, so that is the power dissipation. So that is 11.25, which is quite high, right? So most of the power gets wasted in the form of heat in the load resistor itself. Okay, so that's the waste power. Okay, all right. So that's about problem number 1, okay, which is related to series wire class A power amplifier. Okay, all right. Okay. Now let us come to the second version of class A power amplifier circuit, which is called as transformer coupled class A power amplifier. Okay, transformer coupled class A power amplifier. Okay. Um, okay. So in the disadvantages, while explaining the disadvantages of series wide classic power amplifier, somewhere I had mentioned that the circuit is suffering from low impedance matching. Okay, low impedance matching. Now, due to this low impedance matching, what happens is that the maximum power delivery doesn't take place, and due to which the conversion efficiency drops significantly. Okay, you can see that the maximum possible conversion efficiency is about 25%. All right. Now, if you look at this particular problem itself, okay. Now, let's say you want to find out the amplifier's output impedance. Okay. Now, roughly the amplifier's output impedance is Rn. Okay. The amplifier's output impedance is roughly Rn. And if there is any mismatch in the load, okay, what happens is that there won't be impedance matching. Okay, so this problem can be overcome, okay, using a transformer. Okay, using a transformer. Now let me just give an example. So refer the circuit above. Okay, the previous circuit, this problem circuit. Okay, this is the circuit. Refer the circuit above. If let's say under no load condition, okay, because you see in electrical engineering or even in electronics, normally we don't attach the load to the circuit while carrying out the analysis. That's because the source side, okay, the source side circuit will not change. However, the load can change. The best example what I can give is, the distribution transformer, which is feeding the nearby locality. The transformer parameters remains the same, whether one house load is enabled or 10 house load is enabled or all the houses load is enabled. Whatever may be the load condition, the parameters of the transformer will not change. Okay, similarly, whatever may be the load, it could be a 16 ohm speaker or 8 ohm speaker or 32 ohm speaker or whatever it may be. Okay, the amplifier circuit parameters will not change. Okay, so taking that as the reference, okay, under no load condition, that means to say I am isolating the load from the amplifier circuit. Okay, I can roughly say that output impedance, okay, I can say that output impedance of the amplifier circuit is R0, and which is about 40 kilo ohm for C configuration, right? Which is about 40 kilo ohm for CE configuration, and it is about 2 mega ohm for CB configuration. Okay. Now let us say this is my amplifier network. Okay, I'm just drawing the output side. Okay, say this is EAV and then VI. Okay, don't worry about it. This is the VI, and this is the source signal connected to VI. Okay. Of course, they won't ask this in externals, but for your understanding, I'm telling this. So this is my R0. And what is my R0? Okay, this R0 is nothing but this. So let me write this as Z0 so that I will not confuse you with two R's. Okay, now let us connect the load. Okay, so load can be anything, as I was saying. If you look at your headphone, few headphones may have 8 ohm impedance, few may have 16 ohm, few may have 32 ohm. Okay, so this is your RF. So every user will keep on changing this RF depending upon the headphone specification value. Now, this headphone, whatever it may be, whether it is 8, 16, or 32 ohm, this headphone will always have an impedance value in the range of few tens of ohms. Okay, so your headphone will have an impedance value in the range of tens of ohms. However, the amplifier will have an impedance value. The output impedance of the amplifier will have it in a range which is in the range of 40 kilo ohms. So source impedance is 40, load impedance is 10. That's the reason there exists a huge impedance mismatch. So huge impedance mismatch in series fed class A power amplifier. And that's the reason, as a consequence of this, the conversion efficiency drops. Okay, that's because only a small part of the power is supplied from source to the load. Hence, you can observe dipping efficiency. Okay, now how do we overcome this particular problem? This problem can be overcome if somehow, if you could match the source impedance with the load impedance. Okay, so you need to use impedance matching device. Say for example, transformer to achieve this. Impedance matching device like transformer is used to achieve this. Okay, is used to achieve that. So that's the reason in the circuit what we are going to discuss. Okay, there is transformer coupled class A power amplifier. You will find a transformer on the output side. Okay, so let me first draw the circuit diagram and then let us get into the analysis part. Okay, so this is your base resistor. Emitter, which is held at ground. Now, in case of transformer coupled class A power amplifier, okay, you will not find a load resistor on the collector terminal. Instead, you will find the winding, okay, the primary winding of the transformer. Now, the secondary winding of the transformer is then connected to the load. Okay, the load is normally the speaker. So your speaker. Okay, let's say the load value is R, and let us write down the turns, respective turns N1 and N2, primary and secondary. This is your base resistance RB. Okay, and this is your coupling capacitor C, and this is your input signal V. Okay, all right, and this is the secondary terminal voltage, and this is the primary terminal voltage V1. Okay, RMS value, this V1 and V2 simply represents the RMS value of the device. Okay, now RL is the load resistance, and RL is found in the secondary winding of the, on the secondary side of the transformer. Now, in order to calculate the analysis, okay, what we can do is, you can always make use of something known as the transformation ratio. So what we will do, see, it's something like this. If this RL were to be on the collector side, you could directly apply KVL, isn't it? So that's what we are trying to do. So what we will do, we will try to refer this RL onto the primary side. Okay, and that referral value, let's take it as RL dash. Okay, now I just wanted to know, have you studied about the referring the impedances from secondary to primary and vice versa in transformers and generators? Can anyone tell me?
Yes, sir.
Okay, then I think I can skip off that. So whenever you refer, okay, so refer RL from secondary to primary. Okay, secondary to primary. So when we do that, we will write it as RL dash. Okay, so RL dash is basically K squared into RL, where K is N2 by N1, the transformation ratio. Okay, whereas in few books they will also write RL dash as RL divided by N square. Remember, N is equal to N1 by N2, which is called as turns ratio. Okay, so there is a difference between transformation ratio and turns ratio. So turns ratio is always N by N2, and transformation ratio, you know that, right? It is derived on the basis of, the input VA of transformer is equal to output VA of transformer, and you can get the expression. Okay, so few books says RL dash is equal to RL by N square. Few books says RL dash is equal to K square RL. So you have to understand K is basically reciprocal of N and vice versa. Okay, so by choosing appropriate the primary terms and secondary terms, it is possible to match the load resistance. Okay, load resistance to the output impedance of the amplifier. So let me write it by properly choosing the turns ratio or transformation ratio. No, turns ratio, because I have written both the expressions, right? Turns ratio. One can match the load impedance with the output impedance of the amplifier circuit. Amplifier circuit. Okay, so by matching this, you will be able to achieve a higher frequency. That's what is the discussion now. Okay, all right, so fine. So let us get into the analysis. All right, now before actually getting into the analysis, let me solve a simple problem. Okay, how exactly this transformer is helping us in achieving the impedance matching. Okay, all right, write down. The load of 4 ohm is connected to the secondary of a transformer. Load of 4 ohm is connected to the secondary of a transformer having primary turns of 200 and of 20. Calculate the reflected load impedance on primary. Calculate the reflected load impedance on the primary. Satish Kumar.
Yes, sir.
Try to keep it in mute, okay? All right. So you need to find out RL dash. Okay. Now, before impedance matching, let me write before impedance matching. This is not the part of the problem, but I want you to, compare. So before impedance matching, if you were to look at the Z naught of amplifier, okay, of course it will be in, several kilos of ohms, and RL will be in a few ohms, right? 4 ohms they have given. So you can just write this as poor impedance matching. Okay, so this is the present case scenario. Okay, now let us look at the impedance matching. Okay, so let us write after impedance matching. So that you will be able to assess the role of impedance matching. Now, we know that RL dash is basically K square into RL. Okay, and K is N2 by N1 square into RL. Just a minute. From secondary to primary, it should have been vice versa, right? This should have been n square, right? From primary to secondary, it is K square into R. Okay. And from secondary to primary, it is vice versa. So this is K square. Okay. So K is 1 by K is N, so that is N1 by N to the whole square. So N1 is 200. The whole square into RL. So this is 10. So RL dash is 100 into 4, or it is 400 ohms. So RL dash is 400 ohms. So therefore, after impedance matching, okay, if we were to compare the impedance level, so Z0 of amplifier will not change, okay, because it's a source. So Z0 is in kilos of ohms, but now RL been increased to 400 ohms. Earlier it was 4 ohm, now it is 400 ohm. That means to say, way better than the previous case. You can say that the impedance has been magnified by a factor of 100, right? So due to this improved impedance matching, okay, you will find higher conversion efficiency. Okay, in the sense, due to the better impedance matching, you can expect that the source will be in a position to deliver more power to the load. Okay, so this let us analyze, okay, with the help of the circuit analysis. Okay, all right. So the circuit I have already drawn. So now let me write the analysis. Okay. Now, in the analysis, okay, first let us carry part A, that is DC operation, because through the transformer, the AC current as well as DC current flows. Okay, DC current flows. Now, for DC operation, you can say that, okay, let me write, for the flow of DC current, R1 or R primary, let me write primary winding resistance of transformer is very small. Why is it? See, the impedance, the primary impedance, Z primary, can be written as R primary plus J into XL primary. So you know that for DC current, this inductor acts like a short circuit. Hence, the inductance part will be 0 for the DC current, and therefore Z primary is equal to R primary, and your R primary is very, very low. Okay, the primary resistance of the transformer is very, very low. That's the reason, for the flow of DC current, R primary of the transformer is considered as very small. In fact, you can consider it as 0 ohm itself. Okay, 0 ohm itself. So therefore, load line. Okay, you can construct the load line. Okay, your normal equation for load line, that is the transformer transistor output equation, is VC is equal to VCC minus IC into RC, right? In this case, there is no RC. You have primary winding resistance of the transformer. Now, you had seen that the primary winding resistance, okay, is 0 ohm, is 0 ohm. Okay, so what you get is VCE is equal to VCC when you take IC is equal to 0. Okay. However, IC is equal to VCC divided by R primary. Okay, that is VCC divided by R primary. So R primary, what are we going to take? The ideal value as 0 ohm. So anything divided by 0 is infinite amperes. So basically, current through the transformer, in case of ideal winding, for the flow of DC current, going to be very, very large. So ideally it is infinite ohm. So when we draw the transistor output, when we draw the transistor load line, this is what we'll get. Let me slightly increase the scale. First, let me draw the output characteristics. Okay. So how am I going to draw the DC load line? So this is your y-intercept and this is your x-intercept. Okay. So this is your collector current and this is your collector diameter voltage. Okay. So there is x-intercept which is at VCE is equal to VCC. Okay. Let us write down. So this is your VCC. Okay. Now, where is the y-intercept? Y-intercept is at infinite level. That means to say, you know, you will have a line parallel to y-axis. Okay, that means to say it should not cut the y-axis, because if your DC load line cuts the y-axis, then you will get a finite collector current, but you are supposed to get an infinite collector current. So that is possible only if the line is drawn parallel. Okay, so this is your DC load line. This is your DC load line. It simply says that you know, there won't be any collector current because collector current is infinite. So mathematically, this infinity phenomena exists if the two lines are not intersecting with each other. Okay. Now, when you draw this DC load line, you know, it is going to intersect the transistor output characteristics. So based on, you know, the intersecting location, you can select the operating point. Okay, so this is my operating point Q, and the coordinates of operating points are VCQ and ICQ. Okay, so VCQ is VCC itself, and ICQ, okay, going to be somewhere here. Okay, ICQ. Once that is done, what you can do is you can draw two equidistant points. Okay, one above the Q point and the other below the Q point. Okay, and then you can just draw the, then you can just draw the guidelines. Okay, so this is where your collector current exists. This is your collector current. Okay. Now, I want to draw the voltage. Now, the voltage is not that straightforward. Okay, provided, you know, you go for AC operation. So what I will do to draw the output voltage, I will consider AC operation. AC operation. Okay. So in the AC operation, okay, 922, still time. In the AC operation, what we can do is we can write down, okay, take RMS values. Take RMS values. Okay. And then let us write down the equation as VCE, okay, is equal to instead we can write PAC is equal to V1 RMS into I1 RMS. Okay, I think V1 I have already marked. Correct, yeah, V1 is here. So this is I1, the primary current, and this is I2, the secondary current. Okay, the RMS values. Okay, V1 RMS into I1 RMS. Okay, this also can be written something like I1 RMS square into RL, or V1 RMS square divided by R. So that is the power equation of AC. Okay. Or in terms of RMS value, you can also write PAC is equal to V1 maximum divided by root 2 into I1 maximum divided by root 2. Okay. Or it is V1M I1M divided by 2. Okay. Or in terms of current, you can write I1M square into RL divided by 2, or V1M square into RL. Okay. Since we are considering power delivered to the load, so you can take RL dash. Okay, everywhere you can take RL dash, because RL dash is the referred load resistance on primary side. Okay, on the primary side. Okay. Now, this is about the power. So how will you draw AC load line? AC load line. So this is not drawn on the basis of equation. Okay, this AC load line is drawn. You can say with logic. Okay. Now the AC current will flow through RL dash, right? The AC current will flow through RL dash because we have taken RL dash as the, see here, RL dash as the load resistance referred on the primary side. So obviously this AC current I1 will flow through RL as well, right? So what we will do, therefore, slope of AC load line is M is equal to minus 1 by RL dash. This is a known equation, right? This is a known equation. Whenever there is resistance, the slope of the line is calculated as the reciprocal of the resistance. And our resistance is RL dash. Hence, I have written slope as minus 1 by RL dash. So what you have to do is you have to draw a line. Okay, let me write it here. Okay, so draw a straight line such that slope of the line is M is equal to minus 1 by RL dash, passing through the Q point. Passing through the Q point. Okay, so let's do that. Okay, so what you have to do is you have to draw a load line such that that line passes through the Q point. Something like this. Somewhere here. Okay, so I have to draw one more line. Okay. So this is my VC. Okay. Key point. Okay. Now this is your AC load line. Where PM is equal to minus 1 by RL dash. Okay. Now to draw the waveform, now you will get the equidistant points. Okay. One above the Q point and one below the Q point. Now what you do is you can just draw the guidelines. Here and then from the VCC value, and then from this. Okay. So once you have this, you can draw the voltage waveform. Voltage waveform. So this is IC max. This is IC minimum. This is VCE max. Okay, and this is VCE minimum. Okay, VCE minimum. Okay, so this is what the load line looks like for a transformer coupled class A power amplifier. All right.